Another definition, given a sequence, an infinite sequence that is, we will say that this infinite sequence is increasing, provided the n plus first term is strictly bigger than its predecessor. Not sometimes, but for all values of n instead of natural numbers. And likewise, I will say that the corresponding sequence is decreasing provided the nth term is strictly less than its predecessor. Here too, not sometimes, but for all natural numbers n. Now take a peek at this sequence. To determine whether or not this sequence is monotonic. When I use the word monotonic, I mean the same way you used it back in first semester calculus. If my sequence is strictly increasing or strictly decreasing, one or the other, then I might say it's just monotonic. So question, is the sequence monotonic? And if it is it decreasing or increasing? Well, actually, you know what, everybody? I just messed up big time. This is a really good example, but you might have to break up the two examples. I'll call that example number 2, and let me do a simple example first. Let's suppose I have a sequence where the nth term is something, I don't know, how about this? 7 over n squared plus 1. So before I get to the more sophisticated question, notice how this is a very simple question to answer, because this is what my a sub n looks like. Then I think, algebraically speaking, it's a piece of cake if I just compare a sub n plus 1 to a sub n. So let's compare. I think I could do it without any fancy tricks. A sub n is that. A sub n plus 1 is this. Now let's just purely algebraically compare them. Got two fractions? The numerators are the same. But this denominator right here is larger than this one, so this whole fraction is going to be strictly less than that fraction for all natural numbers n. That being the case, doesn't that basically imply that this is a strictly decreasing sequence according to my definition on the other side of the board? So unlike the question I was going to ask, notice how this one's much easier to answer because these numerators happen to be the same. I can make an easy algebraic comparison with those denominators and therefore make the corresponding comparison with the fractions. Notice, however, with the question I originally asked, which I now label as number 2, to answer the question the way I just did with question number 1, it's not so easy. After all, if you just assume for a brief moment, even though it's not true, if you assume these denominators are the same, again, given that this numerator is larger than that one, here's the direction of inequality. But I think likewise, if I assume the numerators are the same, even though they're not, given that this denominator is larger than that one, forces this fraction to be smaller than this one. I was just trying to press upon you with this more sophisticated question. I can't answer the question directly or algebraically. So I think I need better tools to determine whether or not I'm monotonic. So can you just watch me real quick to make a mistake? One thing I could do is to differentiate this. And if I differentiate, build a number line and find out that for all values of n, 1 or bigger, that my derivative is always negative or always positive. Doesn't that mean the corresponding sequence is always decreasing or increasing respectively? And so if I differentiate this with respect to n, so my denominator times the derivative of my numerator, which is and I think there's my big blunder. I can't differentiate because the n is a discrete variable. It simply obtains values from 1, 2, 3, 4, 5 on up. It's not a continuous function. And so I can't differentiate as such. So here's what I'm going to do instead. To make this all legal, not commit a grave mathematical sin, I'm just going to make a function up out of thin air that I can differentiate, but that agrees with the nth term of my sequence for all natural numbers n. Now that I've expressed the output of a function as a continuous function, which agrees with my sequence when x is restricted to natural numbers, I can differentiate. And so let's do it. No tricks this time. There's only one critical number. That would be 0. And certainly if x is positive, this expression is positive. That means the first derivative function is positive. And if x is negative, we just don't care because we're only looking at values at 1, 2, 3 on up. And so certainly the original function is increasing to the right of 0. Therefore, this corresponding sequence where n starts at 1, then goes on up, is monotonic, and in particular, an increasing sequence.